Welcome to our week 6 video on the normal distribution and standardized scores. Today we are going to talk about the normal distribution. We'll start by reviewing what we talked about last week quickly. We'll go over the objectives for the video. We'll get into the substance for the week and then talk about what is on deck for next week. So last week we talked about descriptive statistics. In doing so, we learned how to differentiate among different types of data. We talked about categorical data, such as student race and ethnicity, student sex. We could talk about different class types. Those are all examples of categorical data. We also talked about examples of numeric data, and those could include test scores. They could include at the school level, the percent of students who qualify, for example, for special education. Those are numeric data, data that are real numbers. We also talked about how to best depict our data using basic visualization. So we looked at examples of histograms for numeric data. We also looked at pie charts and bar charts for categorical data. And then, of course, we had Dr. Davis come and show us a very cool way to depict categorical data, that is, the paths of people into the superintendency. And those were called alluvial diagrams. We also talked about how to describe our data. In other words, what are the central tendency and how much variability there is in a particular variable's distribution. So those measures of central tendency were mean, median, and mode. And the measures of dispersion that we talked about were range, variance, and standard deviation. If you still have questions about variance and standard deviation, I encourage you to watch the short video that is posted on Blackboard. And last week, we've also learned, we had our first experience with SPSS, and we used it to describe our data. So we used it to pull up some basic visualizations and to describe the central tendency and variability of a couple of variables. Today, the purpose is to talk about the normal distribution. So hopefully by the end of this class or this video, you'll be able to explain what the normal distribution is and why it matters, and explain what it means to standardize a score and when and why we would ever do that. So starting with that first point, what is the normal distribution? We talked a little bit about this, but now we're going to really dig into some of the details. So this is a depiction of a normal distribution. So essentially it's the shape of the distribution of a variable. So in this case, we have a variable here, and it is shaped more or less like a bell curve. So that's what we're talking about here. The normal distribution has a couple of neat characteristics that make it unique, and we're going to go through each of those. The first is that a normal distribution is symmetrical around the mean. And so obviously what that means is that what's on one side of the mean, which is in the middle, is identical to what is on the other side of the mean. That also means that it's what we call unimodal, which just means that there's only one mode. Remember, the mode is the most frequently occurring observation. So there's only one. Sometimes in a distribution, there will be more than one. In a normal curve, there's just one. Another nice characteristic that stems from the fact that it's symmetrical is that the mean, the median, and the mode, by definition, are always going to be the same. So if the mean is 5 in a normal distribution, the median will also be 5, and the mode will also be 5. As we saw in the example of mean and median salary in the US, we know that's not always the case. And of course, symmetrical around the mean also means that it's bell-shaped. So this normal distribution will always have something like this shape. Continuing with symmetry, we have measures for how to know how symmetrical the distribution is or how not symmetrical it is. So for example, our distribution can be skewed. So we have this measure called skewness, and it is of course the extent to which a distribution deviates from perfect symmetry. So it's pulled in one direction or the other. And then kurtosis refers to how pointy the distribution is, or conversely, how flat it is. And there's two different kinds of kurtosis, and I will show you what those look like. So here we have skewness first. So on the left side, we see a distribution that is left skewed. And that is because there's some very low scores that are pulling it to the left. And then on the other side, we see a distribution that is right skewed or positively skewed. And that's because there are some observations that are pulling it to the right. So this would be the example of salary in the US, or if we recall, we have a couple people, that 1% making a lot of money, and they pull that distribution to the right. This is kurtosis. We have our mesokurtic would be considered a perfect bell curve, a normal distribution. A platykurtic is very, very flat. So there's a lot more variability around the mean. And then leptokurtic is when those values, those observations are clustered around the mean. So it's very peaked, it's very high. The second characteristic of the normal distribution is that there's what we call a family of curves. So there's not just one normal distribution, but rather there's an infinite number of normal or standard curves. And that's because you can have lots of different means and lots of standard deviations associated with that. And it's not just one that the mean is always the same, and it's always the same standard deviation for it to be normally shaped. There are different curves, again, because of those mean and standard deviation. And we have a fancy denotation, of course, to describe a normal distribution. And it is X follows a normal distribution with a certain mean and a certain standard deviation. So that's what that means. If you see that in a textbook or in a paper, then you can remember this amazing slide and know what it meant. The third characteristic is that we have this special curve. So we have all those other the infinite number of curves, but then we have one that's very, very special. And we call this the unit normal distribution. And the unit normal distribution doesn't have the variability that those other normal distributions do. This one always has a mean of 0 and a variance, and therefore a standard deviation of 1. The nice thing about this unit normal curve is that we can calculate what's called the z-score, which we will do a little bit later. And the z-score tells us the number of deviations above the mean a particular score falls without ever referring to a unit. So it's not 5 points above the mean. It's one standard deviation above the mean. And the way that we calculate the z-score is we take the value in a distribution. So let's say they're talking about scores, somebody's score, we subtract from it the mean, and we divide that difference by the standard deviation. So mathematically, what the z-score is that it's the variable's deviation score. Remember that difference, we call the fancy name deviation score. We divide it by the standard deviation for the distribution. Conceptually, a z-score just tells us how far above or below the mean of 0 an individual score or value is. A fourth nice characteristic is that with any normal curve, not just the unit normal, any normal curve, we can determine the area under the curve. And by that, I'm referring to the fact that between 1 and a standard deviation above and 1 standard deviation below the mean, that area includes 68% of all the individuals in your distribution. Likewise, 2 standard deviations above and 2 standard deviations below the mean comprise 95% of all of the individuals in your distribution. And that is true for all normal distributions. And that's really nice to be able to say that. 5, we can transform any normal variable to a unit normally distributed value, which is again a really nice thing to be able to do because, and this gets again into z-scores, because it takes that unit out. So for example, if we take students' test scores, we could transform them from following a distribution of x follows normal distribution with a mean of 85 and a standard deviation of 12.7. We can convert that or transform it to follow a unit normal distribution with a mean of 0 and a standard deviation of 1. So we do that by creating z-scores, but why would we do that? We would do that, again, to take away the particular unit, which lets us compare. So later on, we'll go through the example of comparing SAT scores and ACT scores. They are not the same unit, and unless you convert them, you really can't compare. 6, there's a constant relationship with the standard deviation. And what that means, again, is that the area or percent of the distribution within each standard deviation is going to be the same for all unit normal distributions. So if you look at that little diagram, we see, again, that 68% in the middle, and then that bumps out at the 2 standard deviations above and below to 95%. Finally, points of inflection and this neat word, asymptotic curve. For anyone who's taken some advanced level math, asymptotic, and for those of you who haven't, it just means that a curve approaches but never touches a straight line. So the curve is that tail of the distribution, which is always approaching the x-axis into infinity and never touches it. What that means is that there's always sort of this potential for really extreme scores. They're always possible. They're rare, but they're possible, and that's really important. That gets into the when we talk next week about probability, there's always a chance that an extreme score could occur. So for the distribution of z-scores, we have something called the unit normal table, which gives all the z-scores and the probability of observing those z-scores. And the table, you can find a copy of it in our course resources. There's a PDF, and we'll talk more about this next week when we talk about probability, but you can go in and take a look at that table. All right. Number 2, how do we standardize scores, and when and why would we do this? So standardizing scores is just what it sounds like. You take out that unit, and it makes a particular score comparable across different scales. And of course, that example I gave was the ACT and the SAT, but you could also use it to standardize STAR scores across tests and years. Those tests change, and across the years, things change, and the scaling is what makes them, or the standardizing is what makes them comparable. So to do that, it's our z-score. So we're looking at the deviation between a value in our distribution and the mean, dividing it by the standard deviation. So if we look at the question of an ACT score of 26 and an SAT score of 640, which is better? So what information do we need? We need the mean and the standard deviation for each group. And I have those. In this case, you can see them right there, 590 and 50, and then 22 and 3. And so we can go ahead and apply it. We get a z-score. 640 is a z-score of 1, so 1 standard deviation above the mean. And then we see here that a z-score for an ACT of 26 is 1.3. So it's higher, right? It's 1.3 standard deviations above the mean. So what does that mean practically? Again, it lets us compare across those different scales. And they're also associated with probability, which we'll talk about more next week, which tells us the likelihood of observing a particular value. Some values in the distribution are more likely to be observed than others. So these are our key questions again. So hope you feel pretty good about these. And here's a preview of next week. Don't forget your homework assignment You have some reading to do. You have an online discussion board post, and we're online next week.